Hello again. Welcome back as we continue our discussion of the topology of R. So, in our first lecture in this series, we talked about what it meant to be a neighborhood, an epsilon neighborhood of a point. So, just to remind everyone of our notation, right, if you have a point x and you have a small, presumably, although it doesn't have to be small, but for everything we're going to be doing sooner rather than later, better get used to the idea of epsilon being small. We could move a distance of epsilon in each direction, and that would form an epsilon neighborhood. So essentially, we're going from x minus epsilon up to x plus epsilon. Notice that we don't count the endpoints, so all these neighborhoods are open sets, the way we define them in our last video. And we also talked about deleted neighborhoods. So the reason for reviewing all this is because we'll definitely need deleted neighborhoods in what we need to talk about today. So a deleted neighborhood of x is a normal neighborhood, but we delete the x. And we write, instead of in x semicolon epsilon, in star x semicolon epsilon. So the little star means we've erased the x at the center. So what we really have are two intervals, from x minus epsilon up to x, then from x to x plus epsilon, and we don't count the x. Okay? So that's going to be important because these deleted neighborhoods show up in our next important definition, which are accumulation points. And if you start to think about the name, you can see that we're definitely getting closer and closer to the idea of a limit. So a limit, is things are building up towards something. Okay, accumulation points is a similar sort of, at least sounding name, that things are headed somewhere, that they're piling up somewhere, they're accumulating somewhere. So a point x is an accumulation point for this set S if for every epsilon the deleted neighborhood around x of radius epsilon intersected with S isn't empty. So there's something in that deleted neighborhood. Okay, so why do we need the deleted neighborhood? Well, remember, x, presumably might be a point of S. So we want to erase the x from our neighborhood and still have something inside that deleted neighborhood, which is still in S. In other words, you think about what an accumulation point should mean that points in S are all getting close to X. And so if there's lots of points of S getting close to X, that means that if you look at a neighborhood of X and you throw away X itself, then what's left should have points of S in it. And that's exactly what this says. The deleted neighborhood intersected with S won't be empty. So the set of all the accumulation points of S, we have notation for that. We'll denote that with S with a little prime. So that's S prime. Like derivative prime, only this doesn't have anything to do with derivatives other than the fact that we're going to be seeing accumulation points for the rest of the course, because they're going to show up in what we need to talk about limits and things getting close together. But this isn't exactly having anything to do with derivatives. This is just notation. The accumulation points of S will denote by S prime. Now, suppose you have a point which is in S, but it's not an accumulation point. Then we'll call X an isolated point. Okay? So it's all by itself. So it's in S, but it doesn't have anything else in S anywhere nearby. Right? The closure of S would be S, and then you throw in all of its accumulation points. Now you might want to know why you call it the closure, and well, it's because it's closed, and we'll see why that happens in just a second. But if you take S and you throw in all of its accumulation points, essentially what that means is we're throwing in all the boundary. Then what we get is a set which will have S and its boundary in it, and so that will be closed. Okay, this definitely needs some examples. So let's say that S is the set from -4 to 2, union 3 to 5. And we count the -4 and the 5, but not the 2 and the 3. Right? Then what would the accumulation points be? Well, everything in the middle, all the interior points, are definitely accumulation points. If you're at a number like 0, right, there's lots of points in S near 0, because everything between -4 and 2 is inside of S. What about a point like -4? It's a boundary point, right? So every time you take a neighborhood of -4, you're going to hit stuff which is in S, and also stuff that's not in S, but that doesn't matter. The accumulation point definition isn't exactly like boundary, even though it's obviously closely related. The accumulation point definition just requires that every neighborhood hits something in S. So -4 would definitely be an accumulation point because it will hit stuff to the right of it, which is in S, whenever you take a neighborhood around the -4. Same thing for the 3 and the 5 and so forth. And 4, every number in between. Those will all be accumulation points because whenever you take a neighborhood around, say, 3, then it will hit stuff which is in S, anything to the right of it. Right? So then 3 will be an accumulation point of S. So you throw in those boundary points there at 2 and 3, and that's all part of the accumulation points. So the closure then would be the set with all those S with all those accumulation points thrown in. So suppose S looks like the set that just contains the point 6, and then we union in the interval from 10 to infinity. We've seen this example earlier, right? And this is well, this was in the examples earlier, so it would look familiar when we used it here. Because now, what are the accumulation points? Well, obviously, anything bigger than 10 would count, right? If you pick a number like 12 or 13 and you take a little neighborhood around, say 12, then that's definitely going to hit stuff that's in S, right? That will intersect with S and be non-empty. Also, 10 will be an accumulation point because if I take a little neighborhood around 10, then that little neighborhood will hit stuff to the right of 10, which will be in S. So 10 is an accumulation point. But 6 isn't. And the reason is, remember in our definition, we were careful to say that every deleted neighborhood, right, would hit something that was in S. So if I take a deleted neighborhood around 6, say of radius 1, right, because remember, this has to work for all epsilon, so I can just pick a particular epsilon if I'm trying to get a counterexample that S is an accumulation point. So look at the point 6 and take the deleted epsilon neighborhood where your epsilon is, say, 1. So then my neighborhood would run from 5 to 7, but the deleted neighborhood means I erase the 6. So my neighborhood around 6 that's deleted would run from 5 to 7, only it doesn't count the 6 in the middle. And that deleted neighborhood doesn't hit S at all because I've deleted the 6. Right? That was the only point around 6 which is in S. So the interval from 5 to 7, you throw away the 6, doesn't intersect S at all. So 6 is not an accumulation point. There's nothing else in S anywhere near 6. That means that 6 is an isolated point. It's in S, but it's off all by itself, which of course makes perfectly good sense when you think about this. 6 is all off by itself, doing its own thing. None of the rest of the points in S are anywhere near it. Right? Well, what would the closure of S be? Well, you would throw in S and all of its accumulation points. So we do count the 6 in the closure because that's in S, and we also union in all the accumulation points, so we pick up the 10, and of course everything to the right of it. So here's a more complicated sort of example, and again, we're obviously starting to tiptoe our way a little closer to the idea of limits. So my set is the set 1 over n, where n's a natural number. So that looks like 1 over 1, and then 1 over 2, and 1 over 3. So that'd be, half, a third, a fourth, a fifth, a sixth. So if you remember back to, say, calculus 2, what I'm really talking about here is all the points in a sequence, 1 over n. And of course, these points are obviously all getting closer and closer to 0. A half, a third, a fourth, a fifth, a sixth, a seventh. Those all are getting smaller and smaller and closer to 0. So there's some limit things obviously happening here. But you ask yourself, where does this set accumulate? Well, there is only one accumulation point, and that's 0. Because if I take a little neighborhood around 0, a little deleted neighborhood around 0, then no matter how small my deleted neighborhood is, it will intersect something from S. Right? Because obviously I'm getting points that are getting closer and closer and closer to 0. But on the other hand, every point of S is isolated because the only accumulation point is 0, and that's not in my set. So that means that the closure would be this set S, and we throw in the single point or the set containing the single point 0. Okay, so another theorem. Suppose that we have a set which is contained in R. Then the closure is closed. That's pretty obvious. And again, this would be this was things worked out in the in the textbook, but this is obviously going to be closed because essentially what we're doing when we throw in all the accumulation points is we're also throwing in anything in the boundary. So the closure is really just S union the boundary. Okay? Another theorem, right? S is closed if and only if it contains all of its accumulation points. Also, S is closed if and only if S is equal to its own closure. Both of those say essentially the same thing, right? If S is equal to its own closure, that means that when we threw in the accumulation points to get the closure, we didn't add anything. And of course, that means that its accumulation points were already there, which is what part A says. Okay, so I'm not going to prove part B because again, you can see that in the textbook. Let's prove part A though, just to sort of make sure everybody feels okay with this idea. So I'm going to do this one not directly the way we've done the other proofs in this set of lectures, but I'm going to do this with a proof by contradiction. So remember what we're doing. We're trying to prove the implication that S is closed, right? If and only if S contains all of its accumulation points. So if I want to do this one by contradiction, or at least I'm going to do one direction by contradiction. Again, the other direction you can look up in the book. I'm going to suppose that S is closed, but that there's an accumulation point which isn't in S. So I'm assuming P and not Q, right? If you think back to the way we were doing proofs in the notation we used back then. Okay? And of course, that's why we did all that back then, so we could use it now. Okay, so since we have a point which is an accumulation point and not in S, the advantage of doing a proof by contradiction is we've got a lot of stuff to work with. We're assuming that S is closed, and there is this point which is an accumulation point and not in S. That tells us a lot of stuff because if X is an accumulation point, then that means that for every epsilon, then this little deleted epsilon neighborhood contains a point in S. Okay? But that's really cool because what that means is the non-deleted neighborhood, right, has a point in S that comes from the deleted part and a point which isn't in S. Which point is that? Well, that's X because we assumed that X was an accumulation point but not in S. And of course, that's the definition of being a boundary point. The definition of being a boundary point was that every epsilon neighborhood contained a point in S and a point that wasn't in S. In other words, it intersected S and it intersected the complement. So if X is an accumulation point, but it's not in S, then that non-deleted neighborhood, just the N, will contain a point which is not in S, namely X itself, and a point which is in S because it was an accumulation point that has to be in the N star part. Okay? So X has to be a boundary point, and we assumed that X was closed, that S was closed. That means the boundary is contained in S. There's my contradiction. So again, that's just one direction. Obviously, we could make this go the other direction by just putting the statements up there in the reverse order, and you could make the same proof, go the other way. So what this gives us now is a list of things that are equivalent. This is our first example, I think, of a theorem that says the following are equivalent. This is important enough in math that people have abbreviations for it. So they'll often abbreviate TFAE, which means the following are all equivalent. So this is a theorem that I'm stating, right? And the theorem says the following things are all equivalent. The first is that S is open. Okay? The second thing is that the boundary is contained in the complement. Well, that was just the definition of being open. So obviously those are equivalent. Every point is an interior point. That was a theorem that we had in the last video, that S is open if and only if every point is an interior point. Well, if every point is an interior point, then that means S is actually equal to the interior, because remember, int S is notation for the set of all interior points. That's obvious. The second part is just the definition of what it means to be an interior point. That for every X contained in S, there's an epsilon neighborhood that lies inside of epsilon neighborhood of X that lies inside of S. And of course, we also had a theorem last time that said that the complement was closed if S is open. Okay? So all of these are equivalent. Now, this is really, really useful and really important because you should, if you don't have this already memorized, and probably don't on seeing this video, say that for the first time, write this down, because this is important enough that we're gonna need this a lot. I mean, if you're trying to write a proof about S being an open set, or maybe S not being open, either one, all of these things are equivalent to being open. So as soon as you suppose that S is open, then all of these things are true about S, and you can use any of them to start writing your proof. Or if you're assuming that S is not open, then all these things are false. So start with that and try to prove something. This is really important, you know, that all these are the same and that you know the fact that all these are the same, so you can use any of these in your proofs. Also, I mentioned before that if you start Googling open sets and closed sets and looking at other videos or textbooks, you might see other ways that people have defined open. And in fact, you will see more or less all of these different things taken as the definition of open, and then they write proofs to show that the others are equivalent to it. Okay, so this is for open sets. There is another corresponding sort of theorem for closed sets. So the following things are equivalent to S being closed. The boundary of S is contained in S. So of course, that was our definition. S is equal to its closure. Remember, closure is the set of all the accumulation points. So again, that was more or less what that last proof we went through showed how that has to work. You could also say that S has to contain all of its accumulation points, and that the complement is open. Again, that was a theorem from the last video. So this is another thing that you want to have written down in your notes. You want to be able to, for example, state on an exam. You know, not only because you may need to state it on an exam for its own sake, but also because if you're trying to write a proof and you start out by, saying that you're assuming that S is closed, then you can use any of the things on the screen here to then go to the next step of the proof.